Hello everyone, the topic I share today is an empirical study of model-agnostic interpretation technique for just-in-time software defect prediction. Our report is mainly divided into 5 parts. Research background, classifier-agnostic interpretation technique, experimental setup, experimental results and analysis, and conclusions and future work. Software defects will cause errors and unexpected results of software system. Although software quality assurance activities, such as code review, software testing, can effectively find and repair defects in software system. However, under the constraints of software testing resources and software release time, it is unrealistic for software developers to implement comprehensive quality assurance activities for software systems. Software defect prediction is an effective method to improve the efficiency of SQL activities. By accurately predicting the defect probability of program modules in the software system, developers can design a reasonable test resource allocation plan, thereby reducing the cost of the software development and improving the quality of the software. Just-in-time software defect prediction is a fine-grained defect prediction method, and its predicting results is fine-grained code changes. JIT-SDP technique has the following 3 advantages. First, fine granularity. Compared with coarse-grained file, function, or package, code changes contain few lines of code. Therefore, once a change is predicted to be defect-prone, developers can effectively check the code of the change. Second is immediately. Once the developers submits a code change, the defect prediction model can immediately predict the defect probability of the change. Therefore, developers still clearly remember the process of software development when checking the code for changes. Third is traceability. There's usually only one developer for a code change. Therefore, project managers can easily find suitable developers to check and fix defect changes. Due to the importance of JIT-SDP for improving software quality, many companies have adopted JIT-SDP technique, such as Avaya, BlackBerry, and Cisco. Currently, few studies have focused on the interpretability of the JIT-SDP model. The interpretability of model is very critical in the field of software engineering. In the research of JIT-SDP, the need for interpretability of predicting model mainly comes from 2 aspects. First is the last of chest. Developers may ask, why the code change I submitted is predicted to be buggy. In a software analysis system, if the prediction model cannot provide an explanation for the predicting results, the developer may not be able to believe the predicting results of the model, which will hinder the application of the JIT-SDP model in actual software development. Second is about data privacy protection. In the application of the JIT-SDP model, if the code changes submitted by a developer are often predicted as buggy by the model, the developer's job opportunities, salary bonus, and so on may be affected. According to the Article 22 of the European Union General Data Protection Regulation, if the data used in the decision-making model affects individuals or organizations, the decision-making model needs to provide an explanation. The main contribution of this article are as follows. First, we introduce 3 CM techniques, line, breakdown, and shape, to explain the prediction results of the JIT-SDP model. Second, we conducted a large empirical research on 6 open source projects and evaluate the distribution of ranking differences on each feature in different instances. Third, for a given project, we evaluated the agreement of the feature ranking lists generated by the 3 CE techniques. The interpretability or explainability of a prediction model refers to the degree to which human observers can understand the reasons why the model makes prediction. There are 2 main ways to obtain the interpretability of a machine learning model. First, make the decision-making process of the machine learning model transparent and easy to understand. And second is providing an explanation for each prediction result of the model. Now we will introduce the 3 CA methods. Line is a local surrogate model proposed by Ribeiro. The model uses an interpretable machine learning model, such as linear regression, decision tree, and so on, to locally mimic the prediction of the black box model. Therefore, a local surrogate model can be used to explain an individual instance. Assuming that F is a black box model and X is an instance that needs to be explained, the loss function of the line method is shown in the equation. A breakdown is a CA method. For a target instance, breakdown uses a graded strategy to sequentially measure the importance scores of feature. Assuming that X is a target instance with M features, F is a black box model, and the feature importance circle generated by breakdown satisfies the equation, where V represents the feature importance score calculated by breakdown for the instance on the J feature. And the shape calculates the contribution of the feature to the predicted results according to the correlation gain theory. The model interpretation of shape is shown in equation, where G represents an interpretable model, and M represents the size of the correlation. Z and phi represents the shape value of the J feature, which is used to evaluate the importance circle of the feature. The experimental use the public datasets widely used in JIT-SDP research. The datasets contains the defect data of 10 open source projects, which have a development cycle of more than 5 years, research historical data, and a good defect introducing change rate. Table 1 shows the basic information of 10 projects, including the name of the project, the number of changes, the number of defective changes, the proportion of buggy changes, and the development period of the project and the programming language. Each instance in the dataset contains 14 metrics, which can be effectively used to build the JIT-SDP model. So Table 2 describes the name of the definitions of 14 metrics, This matrix can be divided into 5 dimensions, including diffusion, size, purpose, history, and experience. Before building the classification model, we use a cross-validation method to divide the datasets of each project into a training set and a test set. Keyfold cross-validation randomly divides the datasets into keyfolds with the same size, each of which has roughly the same proportion of the defect changes. Then each fold of the data is used as a test set, and the remaining key folds data is used as the training set. Finally, the average value of key prediction results is used as the final prediction performance. After dividing the training set and the test set, we use the random forest algorithm to build a classification model. A random forest is an ensemble learning algorithm based on bagging. It uses decision trees as the base learners and introduces a random attribute select scheme. This paper adopts 3CA methods to explain JIT-SDP model. We evaluate the differences in the feature importance rank lists generated by different model interpretation methods. We introduce 4 evaluation indicators: Candle's toe coefficient, Candle's W coefficient, top 3 overlap, and top 1 overlap. Where Candle's toe is a non-parametric statistical coefficient used to evaluate the correlation between 2 sequences. And Candle's W coefficient is a statistic used to evaluate the agreement on multiple sequences, and its range is between 0 and 1. Top key overlap is used to evaluate the agreement on multiple sequences on top key values. Our first research question is: what are the interpretation results of classifier-agnostic techniques on the JIT-SDP model? To answer Huiqun, we counted the differences in the feature importance ranks of the instance explanations generated by the 3 same techniques. We selected 2 instances, change 1 and change 2, from the project Fabric 8. These 2 instances are accurately predicted as buggy changes by the prediction model and have a defect probability of 92% and 71% respectively. The figure shows the visual interpretation generated by line for change 1 and change 2. The green bar indicates the saga that supports the change of become buggy, and the red bar indicates the sockets that supports the change to be clean. It can be seen from the figure that the 3 most important factors for change 1 to be predicted as buggy are LA, NF, and entropy, and in the remaining 8% probability, the condition SEXP is the main factor for change 1 to have a clean probability. For change 2, condition LT and condition SEXP are the main factors that change 2 is predicted to be buggy. In the remaining 29% probability, the condition at LA is the most important factor for change 2 to have a clean probability. And this figure also shows the example of instance explanation of breakdown. And the figure shows an example of instance explanation of shape. It can be seen from the figures that change 1 and change 2 have different instance explanations. To this end, we counted the differences in feature importance ranks of different instances for each project. The three figures shows the experimental results of line breakdown and shape techniques on 10 projects, and as can be seen from the three figures, the median of different of the feature ranks generated by line breakdown and shape is 3, 7, and 10, and therefore the most important feature of one instance may rank fourth in another importance. Therefore, there are greater difference among the instance explanations, which further reflects the importance of introducing CA techniques into JIT-STP models. And the feature importance rankings generated by CA techniques can provide valuable insights and get developers to design code changes with low probability defects. And our second question is, for a given project, what's the difference in the feature importance rank list generated by different CA methods? The table 3 shows that the feature ranking list generated by any two CA methods have a strong agreement. And the table 4 shows that the feature ranking list of three CA methods have strong agreement and high agreement on top 1 feature. However, they have small agreement on top 3 features. So, this paper will introduce the 3 interpretation techniques, line breakdown and shape, and as the empirical study shows that the CA techniques have different explanations for different instances, and on average, the difference of feature ranks of 2 instances is 3. And the feature ranking list and the top 1 feature generated by different CA techniques have a strong agreement. However, on the top 3 features, feature list of different CA techniques have small agreement. In the future, we will study the agreement of explanations between CA techniques and the CS techniques. And second, different CA techniques have different principle and calculation process, and therefore we will explore the agreement of explanations generated by different CA techniques for a given instance. And the third, we will further analyze the running time of the different CA techniques. Oh, thank you.